Today we're very lucky. We have Ricardo Arevalo from University of Maryland coming here to talk to us about laser disruption mass spectrometry and its usage for space science and planetary science.
Cool.
All yours.
Thank you. Yeah, so I challenged myself to put as many words onto the first slide as possible. I think I did pretty well.
You remember that.
I still have some room. Okay, so I'll use that space next time. Okay, so yeah, so this is the title slide. I thought it was a good opportunity to highlight that the work I'm going to be introducing you to or reminding some of you guys of is, represents an international collaboration that we've had. So across the pond for uh, over 10 years now, personally, with me personally involved. And so I've worked with the Cosmorbitrap Consortium since 2013, and I'll give you guys a little bit of that story with it. So I thought I would highlight it with all your logos. Usually, this is what my cover slide would look like. So normally I like to start by highlighting the work of early career researchers who have really done more work than me towards all of the objectives I'm going to introduce to you today. I really like citing this article that came out in Nature Astronomy, identifying the critical need to engage early career researchers in space missions, especially when we're talking about missions to the outer planets that are going to take decades to formulate and to realize. And so I've had the privilege of working with some very talented early career researchers over the years, and you'll see their pictures when I highlight some of the work that they've done. Let's see if I can get myself out of here. There we go. Yeah, so I'll give you guys, there you go. Caroline said she wanted to see me in a Florida Gator stuff. So I do tend to wear a lot of sports memorabilia, and I was shamed by Thomas for not wearing a soccer jersey. But, so you can capture my essence in this picture when I was in grad school at the University of Maryland. So this is just to give you a one slide introduction to myself, so you can evaluate if I have any credibility. But that's a picture of me at the University of Maryland. I studied what I would call traditional geochemistry. So I was looking at, yeah, there we go. All right, so I was looking at things like this. Anyone know what this is? It's pretty boring. It's a mid-ocean ridge basalt. So I looked at a whole bunch of terrestrial basalts in order to try to understand a little bit better what the Earth's deep interior looks like, both from a compositional standpoint, but also from a structural standpoint. So that's what I got my PhD doing in 2010. And then I was lucky enough to get hired by NASA Goddard immediately after my PhD, right before a 2-year hiring freeze. So it was very opportunistic. And they saw my graduate school research as you do mass spectrometry, you're going to learn that I love lasers. So everything I do has lasers involved. I've got my logo here, my lab logo, which is, you'll see it in the top of every other, and it's got an L in it, which is a laser. So anyway, so they thought I was a perfect fit to lead the development of the mass spectrometer subsystem of the Mars Organic Molecule Analyzer on the formerly known as the ExoMars rover mission, now known as the Rosalind Franklin mission. Right? So in 2017, I had an opportunity to come back to Maryland. They're only 6 miles down the road, NASA Goddard and the University of Maryland. And so the collaboration's tight. But I consulted with my bosses. So if you know the Paul Mahaffey's of the world or the Will Brinkerhoffs of the world, and all three of us thought it would be mutually beneficial for me to go back to the University of Maryland because Goddard wants, coming back to this theme, early career researchers. You guys are more efficient, more cost effective, more focused oftentimes. And so they wanted that pipeline of students, and they saw me as one way to do it. And we've been able to do that pretty effectively. So I've been at Maryland since 2017, but I go to Goddard every week. My students all work at NASA Goddard. So we could like hybridize the logo if we wanted to. So getting back to the talk, right? It was a lot of words on that first slide, but I said, right, so I'm a mass spectrometrist. You'll learn that out, you'll find that out pretty quickly. But what I think is neat about some of the things that we're doing together through this international partnership is that we're positioning ourselves to answer emerging priorities in the scientific realm, by developing technologies in the engineering room. So we're kind of converging those two things together. So the first question we should ask is, in this current moment, what are the emerging priorities of the planetary science community? Put another way, quelles sont les priorités de la communauté? Not bad. I've been studying French for 100 days on Duolingo. It's not very good. It's not very good. They do, they do not, by the way. I was told this might be risky to insert some French into the slides because of this graphic. That's very common online, where France is the only please don't country in Europe when it comes to speaking our language. But I thought it was worth the risk because I think it's symbolic, again, of this partnership that we've built together. So you will see a smattering of French throughout. Okay. Yeah, so if you want to think about science priorities, we can take a look at the present and the past, and NASA does a really good job of creating these very beautiful images of the missions that are ongoing or soon to launch. And this gives some perspective as to where NASA has put their money to advance the current state of knowledge of the solar system. So it's a nice aesthetic way of introducing maybe where we are today. Where we're going in the future rely on these documents. So these are called the Decadal surveys that NASA contracts out. I often use this slide just because even in the US, many people, I would say most people don't know the process by which NASA determines its top priorities. And so it's not NASA that does it, right? They contract this out to the National Academies of Sciences. So it's technically an independent evaluation of the current state of knowledge and where we want to go in the next 10 years. Of course, the planetary decadal focus on today is the one specific to planetary science that came out in spring of 2022, I believe. So it's locally called OWL because of the Origins, Worlds, and Life document, but it highlights what the community, at least before it was published 3 years ago, so really the work was maybe 5 years ago, thought we should be spending most of our time and money exploring. And certainly Enceladus got a lot of attention in the Decadal survey. It's the #2 new flagship mission behind only a Uranus Explorer, which I'm not as familiar with what the science drivers are for that mission. But this is, #2 again in the flagship missions. And flagships for NASA are over $1 billion. So if you hear the word flagship, it just means it's a dictated mission, which means that NASA, if they have money, they'll say, okay, we're going to pull the trigger and we're going to fund an Enceladus Orbilander mission. There's a lower cost. You guys have something similar at ESA. There's a lower cost category of mission called New Frontiers. And you can't propose to go anywhere you want. So if Thomas wants to go to Mercury to look for tholins, he's not going to convince many people of the value of that. But he also can't propose it to New Frontiers because it's not one of the viable missions that are allowed, right? So this is the list of 7 missions that when the Decadal survey was allowed, that you're allowed to try to respond to. And these are competed. So this isn't NASA saying, we're going to, go to Io. This is once every, theoretically, 5 years, there's an open competition. And if we have an idea to go to Enceladus, for example, because it's highlighted, we have an opportunity to convince the community of it. Now, again, this Decadal was published in 2022. The work was probably 2020. It's been a while. It's already been 3 years since that was published. So NASA had to ask the national academies to update it because the New Frontiers 5 opportunity was supposed to be released in January of 24, I believe. They actually released what's called the pre-release announcement, and then they had to roll it back because of money. So they asked the national academies to reconsider, are these New Frontiers candidates still the top priorities? And most of them are. Enceladus certainly is. So that's one of the takeaways. They did update some things. So the US is spending a lot of money on the Artemis program to explore the moon. So they kind of didn't think that the moon was a hot priority. And I think they thought at the time that Venus was well positioned with Da Vinci. Of course, this was, 6 months ago, a year ago, they were doing this work. Anyway, but Enceladus was found to be a constant. So it's a flagship mission, and it's the only ocean world destination that you're allowed to propose to for New Frontier. So it's getting a lot of press. I don't want to ignore that NASA's weird. Mars has its own thing. It doesn't follow the same hierarchy of missions. They have their own pot of money. And in the Decadal survey, it said that Mars's next priority should be whatever happens to Mars sample return, should be a Mars Life Explorer. So you can see that a lot of focus is going straight to astrobiology. It's not find the water anymore. It's not look for habitable environments. It's really looking for signs of life. So it is kind of a departure. And so if you go to Google Scholar and you look at Enceladus missions, you're going to find a whole bunch of mission concepts that are in the public domain. A number of people in this room are authors on these works, so you'll be very familiar with your own mission concepts. Here are some competitors for you to consider. But this is only over the last 3 years, 4 years, I think. I went to 2021. So again, the community certainly seems to be crystallizing the priority of going to Enceladus. And I could ask you, did all of that introduction feel like deja vu for the Europeans in the room? Because you guys follow the exact same. I did a little bit of research to see how ESA works and what the current state of ESA's priorities are. You guys have your own science fleet illustrations. It's the more cartoonized version that I know ESA really likes. And you guys have your own decadal survey equivalent, right? Voyage 2050 came out in May 2021, where you guys also highlighted the value of ocean worlds and astrobiology. And ironically enough, you guys also asked an independent committee to evaluate what's the highest priority. And the takeaway was the same thing, right? This is copied and pasted. Enceladus, South Polar Lander with an orbiter and plume sampling system would be the optimum candidate for your large class mission. So we agree, right? So the community certainly seems to be very excited for Enceladus in astrobiology objectives. So we know where we want to go, but what do we want to do, right? How are we going to do it, and what are we going to look for? Again, the work has been done for me. I don't need to convince you guys what we need to do if we get a mission to, the Mars Life Explorer or an Enceladus Orbilander. There's a large number of frameworks or paradigms that have been put out there that are meant to inspire conversation and debate about what types of biosignatures, right? Evidence of life, biomarkers, whatever term you like to use, which ones we should be looking for, which ones are the most convincing, which ones are the easiest or the most difficult to make. So the ladder of life detection is probably the one that I hear invoked the most, but there's a bunch of different options out there. This is a graphic I stole from Stephanie Getty at NASA Goddard. This was before the ladder of life detection, but this was her own personal way of having like a modular way of identifying classes of biomarkers and maybe moving them up and down this scale of what's super convincing and what's less convincing. Another way of illustrating this is a graphic that one of my students who just passed her PhD qualifying exam a couple of weeks ago, she created. It was inspired by Marjorie Chan's framework, which puts biomarkers as a function of scales. So just a different way of thinking about it. But whatever your favorite flavor is, all of these frameworks agree on some things. One thing they all agree on is that the more observations you collect, the more redundant proxies, the higher the confidence of your assertion of life or of not life, right? So the more you can see, the more confident you are. And certainly we need to understand what the blank is, right? So abiotic signatures or abiosignatures were highlighted very strongly in the NASA Decadal survey. I don't know if Voyage 2050 did as much service to that, but understanding the complexity and the breadth of organic material that can be produced via abiotic mechanisms is absolutely critical so that we know what's biological or what the probability is that biology created, whatever feature we're looking at. So those are kind of the science drivers. The next question we should ask are what technologies are in development that can support these science priorities? And so I'm a mass spectrometrist. So of course, I'm going to put a graphic up here. This is one of my former PhD students created for a review article we wrote some years ago. It's in Christel's lab. So it warms my heart. It's a little outdated. You can see that it was published in 2020, but we have ExoMars as 2018 here. So it's, it needs to be updated. But the motivation for creating this type of graphic was to try to illustrate that first of all, mass spectrometry has a long history in planetary science, but also you can see from a semi-quantitative perspective that the capabilities more or less progress as a function of time. So modern day sensors, modern day mass analyzers are generally more capable due to innovation in the lab. We often follow commercial trends, but innovation has allowed an increase in things like mass resolving power, mass accuracy, mass range, etc. So one of the things I'd like to focus on today is the value of mass resolution, mass resolving powers. And so this is one of the graphics that we, again, together created almost more than 10 years ago to try to get some NASA funding. And I'll go through that story a little bit more later. But this is a graphic that we put together collectively 10 years ago to try to illustrate the value of mass resolving power, right? So where you might see a single peak in a mass spectrum with a low resolution instrument, if you're able to increase that particular capability, you might find that what you thought was one feature is actually a collection of features. And so from a historical standpoint, we can see where, missions and instruments that we're familiar with, where they fall along this trend line. So the SAM instrument on the Curiosity rover has a mass resolving power in this nomenclature, which is mass over the delta mass that you can distinguish of about 500. It's a unit mass resolution. The MoMA instrument has the same requirement, but it actually beats it a little bit. So they can realize about a mass resolving power of about 1,000. The Rosina instrument was a higher resolution instrument that was almost an order of magnitude higher. And of course, the mass specs instrument that launched on Europa Clipper last November is the highest resolution analyzer that's been flown to date. So you can kind of see it's kind of a progression as a function of time, depending on when you date the development of these sensors. But when we were trying to get NASA to recognize the value of this, one of the questions we often got asked is, well, what resolution's enough? Do you actually need higher mass resolving power than mass specs, for example? And so the burden is on us to convince the community. So how are you going to convince the community? You're going to look at analog samples, right? And see how complex is organic material maybe even in the abiotic realm before we introduce biology. And so here are a couple of examples where we've created analog samples. So here's an irradiated benzene ice, a relatively simple experiment that Michael Callahan at NASA Goddard and that group conducted a number of years ago, and they had to use a high resolution instrument to deconvolve all of the features, all of the peaks that they observed in this analog sample. Well, another good analog material for planetary stuff are meteorites, right? So why not consider meteorites? I love this paper. It's a single extract of a single carbonaceous chondrite, and they found over 40,000 distinct peaks above a signal to noise of 2. So, and this was the mass resolving power of 900,000, but it kind of illustrates that the higher you can increase that mass resolving power, the more complexity you didn't even know was there starts to get revealed. And then there are people that do these Tholen experiments here at LATMOS, and they're complex. I mean, I saw Christel was looking, and Laura were looking at some of your Tholens last week. And again, the spectra are extraordinarily rich. And so it's like we would miss a lot of this complexity. We might not know what to do with it yet, but we would miss all of that information if we didn't have a high resolution mass analyzer. And so if the question is what technologies are in development that are of value, one of the responses, one of the answers I'd give you is an Orbichat mass analyzer. So again, we built this partnership together to try to qualify an Orbitrat mass analyzer for spaceflight. Starting back in 2013 is when I got involved with you all. You guys actually started that initiative a bit earlier. But an Orbitrat is a specific type of mass analyzer. I'm actually going to go back and allow this graphic to go one more time. This is an old graphic that Thermo did, but I keep it because it zooms in nicely. You see 3 different ions here, and they're rotating around this center electrode, and the frequency by which they cross that mid-plane is commensurate with its mass to charge ratio. It's very different than quadrupoles, time of flight instruments, linear ion traps, because you're not like hitting that ion onto something and then physically detecting it. You're using this image current to capture these frequencies, and then you use fast Fourier transform to convert it to a frequency spectrum, et cetera, et cetera. So it works very differently. It was only innovated in 1999. Alexander Makarov patented it. This patent, right? 1999, which if you consider quadrupoles and time of flight instruments, they're 100 years old. The technology was invented over 100 years ago. So it's new in the commercial realm, and it's certainly new to spaceflight. So the second answer I'm going to give you for this, what technologies are in development, are lasers, right? Lasers are getting smaller, more powerful, and more specific for the applications that we're interested in. And they also bring a lot of other analytical benefits to the table. So one is that they don't require physical contact with the sample. So you can reduce cross-contamination if you analyze sample to sample. You don't have to worry about planetary protection as much from an instrument perspective. But something that maybe gets overlooked is that you're using a laser to ionize a sample. Anything that absorbs that UV light, because we typically operate in the ultraviolet, is going to get ionized, whether it's organic, a lot of organics like UV, or inorganic, a lot of rocky things like UV. So you get them together. So you can make measurements of organic and inorganic materials at the same time on a shot-by-shot basis. It's a destructive technique, but it's orders of magnitude less destructive than things that we're maybe more familiar with in planetary science, like pyrolysis, which we typically, SAM looks at tens or hundreds of milligrams of sample. And then you can do some fancy things. If you fly the right laser, right, you can select the wavelength for maybe the class of organic material you're looking for. You can also fly a laser that has more power than you might think you need. And then you can do experiments where you intentionally break an organic. So the way we typically operate lasers for organics detection is you start hitting the sample with your laser with the lowest energy possible, and you slowly increase the energy until you cross that threshold of desorption. And then you kind of sit there. But if you want to, you can crank the laser up and intentionally fragment it, and you can get some structural information. So there's value to how you implement these things. So laser-based mass spectrometry isn't new. You can find it applications in the lab where maybe the biggest benefit is spatial resolution. And so if you go through the literature, some examples of where you'll see laser ablation is to map minerals in different phases in rocky materials. Like I think these are garnets shown over here. Or in the fields, you typically see tissue imaging. So if you're in pharmaceuticals, maybe you'll look at, this is probably a rat brain, and you look to see how long it takes a particular drug to find its way to the targeted area in the brain, and you do these cross sections and you get the spatial resolution that comes with it. When it comes to space and astrobiology, lasers allow us to look for a different type of organic that maybe we have access to. This is actually a really old slide that the MoMA team, which again, I've been privileged to be part of for 15 years, we created this a long time ago to try to compare MoMA to SAM and other instruments, and it's just worth using over and over. So it's an old slide, but it still tells the story. that pyrolysis generally gives us an access to volatile organics. If you consider derivatization, we can start making more refractory organics sufficiently volatile that we can see them through pyrolysis. But the promise of laser desorption, so hitting laser-based mass spectrometry, is that we can directly ionize things that aren't as volatile, things that are maybe more macromolecular, more complex networks of organic pieces, relatively intact to some degree. To some degree, at some degree, you're gonna fragment it, but we have access to that stuff. And so we can go back to my student's example of these biosignatures, and we can superimpose maybe how laser desorption mass spectrometry as a technology and as a novel technique can be applied to the search for these different types of biosignatures. So I'm making this big case for how important laser-based mass spec is. And again, I'm not the first one to make this case, right? There's a laser-based mass spec on the Rosalind Franklin mission. There's a laser-based mass spec on the DRAMS instrument on Dragonfly. The Russians have been trying to land a laser-based mass spec since the 1980s. Phobos 2 launched in 88 or 89. But to date, a laser mass spectrometer hasn't been implemented in space because it's hard. It's hard for a variety of reasons. Technology, politics, money, landing is hard, right? The Russia's most recent attempt to land their instrument was last summer. I watched it closely, and unfortunately, landing on the moon, which we kind of take for granted, is hard. And so they weren't able to land their spacecraft, and so they lost that mission. But there's still hope with MoMA, DRAMS, and the University of Bern got their laser ionization mass spec included on a future Artemis mission to land on the moon. So there's still hope for it. But kudos to the Cosmorbitrap Consortium, because you all recognized the value of integrating a laser with an Orbitrap a long time ago. So you guys came up with this idea of ILMA. And you guys proposed this to ESA, I think, on a couple of occasions that maybe weren't ultimately selected for mission implementation, but they allowed you to build up that first fundamental breadboard that's in Orléans, France, that I'm spending I've been there for 6 weeks. I have 6 more weeks to spend working with the team out there. I had the opportunity to spend a week there in 2018 to use that instrument to try to position ourselves to respond to what at the time was a Europa lander mission that NASA released a pre-announcement of opportunity, and then they rolled it back because of money reasons. We did get money from it. That was good. But I had the privilege to work there. And so you guys have been doing what's the next step? Once you build this technology, you have to convince your colleagues and the greater community how important the science you can get from it, the breadth of scientific products. And so that your group has been producing a lot of publications on it. I was part of some of them, but certainly you guys have been doing a really good job advertising what a laser and an Orbitrap can do together. But our story began in 2013, where we first proposed to NASA to collaborate across the Atlantic Ocean and to build a US-French instrument together. The first proposal wasn't successful. So for the early career people, don't take failure too hard, because just stick with it. We proposed it again in 2014, and we won our first NASA money to build an instrument. So what we've been working on are actually a number of different versions of this instrument, all specifically geared towards a specific planetary environment or a specific biosignature, class of biosignature. So I'm going to talk to you today about corals. It's our highest fidelity instrument. It's gone through thermal testing, it's gone through vibration, and so that is our most flight-like instrument. So the data you'll see today are all from different versions of corals. Some of them are advanced breadboards like ETUs, and some of them are from our flight-like model. But what we did to advertise to NASA, to convince NASA to give us the money, is that we can reach ultra high mass resolving power, so higher than mass spec, higher than 100,000 that over in this mass over delta mass scale, with just as importantly parts per million level mass accuracy. So if we see a peak, we can say how many carbons, how many hydrogens, how many nitrogens are in there if we have a very accurate peak. We've been developing a number of laser solutions. Corals at its the baseline design is a 266 because it looks like MoMA. It looks like DRAMS. So it has that complementarity with it. But some inorganic phases like deeper UV. So we've also built a 213 laser. And so we have different options when we're pursuing a mission to try to win something. And so when it comes to the science, right, we've been using the Cosmorbitrap setup in Orleans. We built a progressive breadboard at NASA Goddard Space Flight Center. So it was something that isn't flight-like yet. So this is NASA jargon here. Form, fit, and function, they like to say. The Cosmorbitrap meets the function, right? The data you get from the Cosmorbitrap look like what a flight instrument would give you. Then we built something smaller. So it looks like it has the potential to be added onto a spacecraft. It's low mass and it's low power. It hasn't been ruggedized. I don't know if that word translates well, but it hasn't been built to survive vibration, but it meets the form factor and it still meets the functionality. And then we built, this is Corals. This is at the University of Maryland. And this is, the scale here, this is a multimeter, if you know what this is. I think the laser is, I just measured it, 18
metric system.
Metric.
centimeters. It's 18 centimeters in height. So it's a very small instrument. The total instrument, the electronics are what's the biggest, but it's under 10 kilograms, 55 watts. So we're trying to find a home for this instrument. But the science we get, again, we get organic. If you're interested in astrobiology, of course, we get the organics. But we also get the inorganic. So we've been, and I'll tell you a little bit more later, but we've been trying to win a mission to the moon because the Artemis program has a lot of money and a lot of opportunity. And there's even astrobiology that we can learn on the surface of the moon. So we're trying to, again, illustrate to the community everything we can do. We've been exploring what we can do quantitatively. So can we measure isotope abundances with sufficient precision to resolve different end members? And then we can get, molecular structure with collision cross sections. Okay, so the next few slides are kind of what we've been spending our time on over the last couple of years from a scientific demonstration perspective, kind of like what you guys have been doing with the Cosmorbitrap. And you'll see the early career researchers, you'll see some faces that you guys are very familiar with. So Anais used to work with you guys, Lori's here, Grace and Somia. Grace is my former student, Somia is my former postdoc, who's still writing up a paper for us. But they were looking at more relevant analog samples. So this was a simulation of a mission scenario where we got 3 milliliters of Enceladus ice, because that kind of mimicked what the Europa lander mission was supposed to deliver, 3 milliliters per instrument. And if it had a roughly chondritic composition for the rocky core. And we convinced ourselves and the community that we can see things like nucleobases, we can see amino acids, etc., at relevant concentrations that simulate this mission scenario. Another cool demonstration, this one's one of my favorites because I learned a bunch about it, was I gave a talk at AbSciCon, and a woman who I've never met before I sat back down in my seat, came up to me and she was like, "Really good talk. Can you measure peptides?" And I was like, "I don't know. I've never tried." But she had this motivation and it blossomed into a collaboration where she works at the University of Washington, and they went to this particular location in Alaska where they have seasonal sea ice. And there's a microbe there called Colwellia CP34H that survives in these ultra cold, high salinity conditions. And they went up there, they sampled it, they brought some of those microbes back, and then they tortured them, right? They subjected them to progressively colder and colder temperatures and higher salinities. And the populations that lived, they compared their proteomes to the populations that died and couldn't survive. And they wanted to see which proteins and which 3 and 4 amino acid peptides were statistically enriched in the populations that were able to survive, thinking that maybe it represents a metabolic strategy or a structural adaptation that allows them to survive these extreme conditions. And so this was before us, but they identified these candidate amino acid sequences, these peptides. And so we tested, can we see this with a laser? Just a laser and just an Orbitrap mass analyzer. And we were able to successfully not just detect the molecular ion, that's relatively easy, but you need to sequence it, right? This is where I had to teach myself about, de novo proteomics. AAG is different than AGA, which is different than GAA, right? So, but the one that's statistically linked to surviving extreme environments is AAG. So you have to be able to sequence it. So you need specific fragments from it. And we were able to do that advanced experiment, see the molecular ion, crank the laser up and break it, and then observe those diagnostic fragments. So it's very cool study. I'm a geochemist, so of course I want to know, can we also identify minerals, rock lithologies, what can we do quantitatively? And so here's an example where we looked at rare earth elements in probably the most well-studied solid material in the world, which is the NIS 610 glass. And we were able to observe and extrapolate detection limits for rare earth elements down to less than 10 ppm, which is pretty good because usually you need a plasma mass spectrometer to measure these things. We wanted to know how well we can measure isotopes. And so this was one of our earlier studies. It was a single scan measurement of potassium 41 to 39. It looked really good. It was a very accurate, but it was a single scan. So it suggested that we could do some quantitative isotope measurements, but we didn't spend the time to build a statistical database. And so that's something that we've been trying to do now, is convince ourselves in the community that we can build the statistics. We know lasers are going to fractionate isotopes. That's going to happen, and that's okay, as long as we can correct for those fractionations. The challenge is that we're learning as the Orbitrap community tries to expand what the Orbitrap can do, even in the commercial realm, that the Orbitrap fractionates. These ions are oscillating back and forth, and if you have a big band of ions and a little band of ions and they cross over, the big band is a bully, and it can kind of mess up the little band. And so this is Amy Hoffman's group at Caltech, and they were trying to look at carbon isotopes, so C12, C13, in some labeled organics, and they were able to measuring the isotopes is easy, they found, as long as you don't have anything else in the Orbitrap. Once you start adding something else in the Orbitrap, you fractionate. And learning how it's fractionating and how you can correct for it is a work in progress. So we've been spending a lot of time on this, understanding what's the best way of characterizing the peaks. Is it a parabolic fit? That's kind of what Alexander Makarov does at Thermo. Is it a Gaussian? Is it Lorentzian? Is it a peak area? Is it a peak height? If you do Fourier transform stuff, you're padding your data with zeros. You're adding these windowing things to improve the peak shape, but they all come at a cost. So we think we found our preferred way of processing the data. These were some data that 3 years ago, Fabrice and Laurent Thurkel came over from Orléans. They came over to the University of Maryland to work on our flight-like instrument. And this is a 40 consecutive scans where we're looking at titanium 48 to 47. So this is a non-traditional stable isotope system. And you can see that there's a lot of jitter in the line, right? There's a lack of reproducibility, which isn't surprising because, again, the laser is going to fractionate. But if we collect measurements long enough, maybe the statistics will be okay. But one of the problems is that it's fractionated, right? So it's not just this variance, it's also that our average, this line here, is different than the true value. So we have to understand how to correct for this stuff. And again, on top of that, that's pretty much, this is the left-hand side is basically the laser driving fractionation. The right-hand side, this is a single scan. We're now looking at a single scan, and this is just time on the x-axis, time slices. So 0 to 100, 100 to 200 milliseconds across an 800 millisecond transient of the orbit trap. And you can see we're progressively fractionating. The longer we observe these ions moving back and forth, we're artificially increasing the observed 48 to 47 titanium ratio. So we have to account for both of these phenomena in order to correct for it. And so we're learning how to do that. So Soumya, who's my former postdoc, she's at Los Alamos now, applied, I forget what her favorite fractionation correction is here, but you can see the external reproducibility now. Our average line is right on top of the natural, right? Here it's not, they're separated, it's 10.071, and now our average is 10.072. So we're finding ways to correct for accuracy. The precision's still something we need to work on. But if you apply that same correction to individual time slices, we can now normalize that slope. And now we don't have a slope, right? It's a constant observation. So we still have work to do, but we're trying to apply isotopes so we can expand the scientific products that we can return with these missions. I have a postdoc who just joined our group last June from JAXA. He is also using our flight-like instrument. He's interested in chemical imaging. We talk about it all the time. I'm guilty of this. I advertise, laser mass spectrometry, you can build chemical images, and then we don't do it a lot. So he's driven to try to demonstrate what our flight-like instrument can do. So the first thing he did was, let's just see if this works at all. He took his finger, stuck it on some green ink, which absorbs UV really well, and he was able to map the little spirals of his fingerprint. Don't take an image of this. Don't steal his identity. This shouldn't go on YouTube. It's okay. He published this at ASMS. But it was a neat little demonstration, but not relevant, right? It's not particularly relevant. So then he progressed. He's like, okay, what's a relevant demonstration of chemical imaging? What about iron meteorites in this Widmanstätten pattern? We have taenite and kamacite, which just vary based on their proportion of iron to nickel. And he's able to use nickel as a proxy to reproduce this kind of cross-hatching between these two phases. So again, a demonstration of the value of 2D imaging, but something else that we hope that this Corals instrument can do, hopefully DRAMS can do it, and MoMA, would be that because you get free information on the inorganic, on the mineral phase, you should be able to do modal mineralogy to construct what's the rock type. Is it a basalt? Is it an andesite? Is it a clay-rich shale? And so he's been doing experiments where he's creating synthetic mixtures. Here it's hematite, an iron-rich oxide, and gypsum, right, a calcium sulfate. And so he looks at pure hematite, pure gypsum, and then he mixes them together, and he has been able to reproduce the modal mineralogy to less than 10% air, which is a pretty valuable outcome, I think, for the demonstration of this. And then I think this might be my last demonstration. So if I'm overwhelming you with information, again, it's just like we have a lot of ideas of how to explore what the instrument can do, because there's just a lot to do. This is my senior grad student, Luke Andrews, and he is very into astrobiology. And he noted that abiotic, insoluble organic matter, so the stuff we see in meteorites, looks a lot like kerogen that we find in terrestrial shales, organic rich shales. So he wants to use laser desorption mass spectrometry to distinguish these two things, because maybe the distinctions between them are biosignatures. And so he's been looking at, again, this is a Green River shale. So this is a terrestrial organic rich shale, comparing it to a bunch of different carbonaceous chondrites. Here it's Aguas Zarcas as a CM2. And he's trying to figure out different ways of comparing all of the peaks, right? There are thousands of peaks there, he can unambiguously assign, you know, a subset, so 500 to 1,000 of them in these single spectra. And so it's figuring out how can we identify, how can we distinguish them, looking at their different proportions of CH versus CHO versus CHN, using Van Crevelen diagrams, so ratios of hydrogen to carbon and oxygen to carbon, and then ways of calculating estimations for how many double bonds might be in there, etc. That's what he presented at AGU next to Christophe Sautin poster, right next to each other. I lied. There's one more slide here. This is Maddie. So she's my youngest graduate student to date. She's less into astrobiology, but she loves Mars. But she asked a question about, you know, Mars has a diversity of minerals on its surface. And if we're looking for biosignatures, cholesterol might be a biosignature. It's a very resilient hopanoid that has been observed. And hopanoids we observe in 1.8 billion year old terrestrial rocks, so they're very resistant to degradation. If this represents a type of biomarker, is it as easy or is it more difficult to detect if it's adsorbed onto different phases found on Mars? And so she asked herself this question, and she put together a project where she built a calibration curve. It's just a sensitivity curve, right? Signal as a function, right? Signal on the y-axis. This is one of the primary fragments of cholesterol. It's the strongest peak for cholesterol versus concentration. And she's doping these minerals herself. And what matters is that the slopes are very different, right? Magnesite has a very different slope and a different intercept. The intercept is just a signal to noise ratio of 3, right? Just our favorite, right? That's one of the signal to noise of 2, 3, whatever your favorite is. And it's very different to nontronite. So it seems that we have different inferred detection limits for cholesterol, the same organic, the same instrument, the same technique, but the minerals have serve as a major control on how easy or difficult it is to observe cholesterol. So here she's trying to convince that her experiments can see relevant levels of cholesterol that overlap with estimations for how much organic carbon's found on Mars. But even her experiments are upper limits of detections because she's using a commercial analog to our instrument, and it has a tiny beam. It's a 15 micron beam. So if you increase the beam to 400 microns, like MoMA, I forget what DRAMS is. I think they're like 150 micron. You get R squared, right? As you increase the beam size, you have more analyte to characterize. So that study is why I'm here for 3 months. So I got supported by Studium to come out to use the Cosmorbit and to understand why, right? Why does Maddie see this? Why does olivine suck? Olivine's terrible. It's really hard to see anything on olivine. But the question is why? It could be a bunch of different things. Does olivine absorb less ultraviolet light at 266? Or is it because it's magnesium rich? The olivine she is magnesium rich, and magnesium is not conducive to, it's out competing for electrons or hydrogens, or I don't know yet, right? Is it something about the chemistry? Is it the thermal conductivity of the mineral or the electrical conductivity? Or is it the work function? It's a bunch of questions. So I'm here for 3 months to try to answer that through some simpler experiments that are simpler, but they'll be a little more systematic to pinpoint what it is. So that's it for the science. That's what we're working on now. That's the present stage. What's in the future? Again, another collaboration that we have is a hybridized instrument, which is called the Advanced Resolution Organic Molecule Analyzer, which integrates a MoMA-like linear ion trap and a Corals-like orbit trap. So this is in development at NASA. Goddard, it's just a couple of years behind. And like I said, something else that we've been spending a lot of our time on, I've been spending a lot of my time on, is trying to find a home for our instrument. It's TRL6, if you're familiar with technology readiness levels, it's ready for a mission. It's gone through qualification. We're expanding how much science it can return, but it's ready to fly. Because there's no New Frontiers opportunity, because there's not a flagship yet to go to Enceladus, the opportunity is to go to the moon. And so we've pitched sending one of our instruments. Corals is just like Crater. The only difference is the laser. And we've been trying to get implemented onto a lunar lander to bring home a bunch of different science objectives, right? So we get A, biosignatures on the moon. We get inorganic information so we can understand how the crust differentiated. And then, of course, NASA wants to know where are the resources, and we can do that for them too. So with that being said, we have some take-home messages. I like the blue one. It says that our partnership transcends stuff, right? It's we've in the last 12 years, we've gone through, political pressure, financial pressures, international tensions, but it's heartwarming to see that science does transcend these things that we don't have as much control. And so it's a pretty valuable demonstration. With regard to the talk, right, LDMS techniques provide access to organic and inorganic information, so they're great for astrobiology, but also a range of other missions. The orbit trap is really what's maybe the most innovative thing that we've been pushing, that you guys have been pushing even since before I got involved, because it brings so much to the table with their mass resolution and mass accuracy. The future work is, again, we're doing it right now, is to try to demonstrate this scientific reach of the instrument as much as possible and try to find new missions and maybe try to develop next generation versions of the instrument like Aroma. So this is, I usually end on this slide because I like to highlight all of the early career researchers that have worked since I came to Maryland. So this is over the last 7 years. Again, some faces you'll see are mechanical engineers, scientists, every discipline. But I thought I'd end with this one because I have some fun pictures of people in this room that maybe they're embarrassed about because it was like 7 years ago. This is when I came out here for a technical interface meeting. I don't remember when. I think it was when I visited here, when there was a creperie in the lawn. Sometime, it's probably like 10 years ago. I think this was maybe for the international workshop that was in Orleans. This is when Laurent and Fabrice came out to the US a couple of months ago. And then Lustudium, I really want to acknowledge Lustudium for supporting me to come out here. I attended the conference that Jan put on in 2018. Alexander was there. You can see Laura's doing her best impression of Alexander. There's Christelle and there's Fabrice playing the sax and Jan playing the guitar, and his wife was singing. It was a good time. Okay, that's all I got. Thank you for your time.